Okay, we're working 4.90 here, assigning oxidation numbers to different atoms within compounds or ions. A lists MnO4 2-. This is an ion, hence the 2-. It's made up of two elements, manganese and oxygen. Because of that, we need to give oxidation numbers to each element, remember, on a per atom basis. When I sum up all of the oxidation numbers for every element in this compound, I need to get 2- because it's an ion, and the rule is the sum of the oxidation numbers or states of all the atoms that make up that ion have to equal the ion. If it's neutral, it has to be neutral. But here it's 2-, so the sum of all these have to equal 2-. Then you go looking for elements that are familiar, that have existing rules. The rule for oxygen, generally speaking, it has a -2 oxidation number. Okay, we have quantity 4 of the oxygens, each at -2. That's -8, which means to make the math work out, it looks like the manganese here needs to be +6. If this is +6, and we've got 4 -2, that's -8 total. Net -2, everything works out. Okay. This one, Mn2O3. Again, you realize first off, is it charged? Is it neutral? It's neutral, so the sum of my oxidation states for all atoms have to be 0. Then I go looking for familiar rules. Well, one certainly exists for oxygen. We're very familiar with oxygen being -2. Almost always that will be the case. Peroxides are only the exception. Okay, so we got -2 for that. What about the manganese then? Well, I've got 3 copies, each at -2. That's -6 total. And I've got 2 of these manganese. So I think to make this work, if I make each manganese a +3, and I've got 2 of them, that's +6 total. And that can offset these -6s, okay, or the -6 from the 3 atoms of oxygen. So it works algebraically, all right? Last one. Chemical compound known as potassium permanganate, KMnO4. This one's got 3 elements, manganese, oxygen, potassium. The whole thing together is electrically neutral or uncharged. Okay, so what elements do we know about here? Well, clearly we've been working this oxygen being -2 business for a while here, and I think that's going to be conserved here. That's the most common oxidation state by far for oxygen. We also have this potassium. That's a group 1 metal. Generally speaking, those guys are +1. Okay? So we're making some progress here, okay? Let's kind of see where we're at and what we need to make manganese to make the whole thing be electrically neutral. So I've got 4 copies of oxygen, each at -2. That's a -8. And I've only got 1 positive right now, right? So it seems like this 1 manganese that I have, that needs to be +7. To couple with this +1, that's +8, and then that'll offset my -8 from the oxygen. If I do that, it works out as being electrically neutral, okay? So here we have a situation where we see manganese, the same element, take on many different oxidation states in these 3 examples. And that's pretty common, actually, for a lot of elements on the periodic tables that don't have the hard and fast rules that we learn about. So transition metals, things around nitrogen, phosphorus, nonmetals from the periodic table, they can have different oxidation numbers, and that's pretty common. So that's why we need to really practice these rules, practice assigning oxidation numbers, so we can get good at it.